Hello, welcome to your lesson on independent events. Just like this dog, some events in probability are quite independent. Let's take a look. So our warm-up today, though, will give you some past exam problems, and these exam problems are taken from old probability problems on exams, and you already have all the skills you need to answer these. So let's see how they goes. Try this one first. Let's check our work. So first of all, it tells us probability of A is 0.3. We can go like that. Probability of B is 0.6. And it gives us the union, which is all those combined there, is 0.7. So with those values, we should be able to get everything. Write down the value of T. Write down means no calculation necessary. It's so obvious. And T is out here. So if all of this blue is 0.7, then out here it must be 0.3. Because all in total, we have 100% probability, right? So that's why it said write down. 0.3. Next, show. Show that means you have to show some work. It gives you the answer you're working towards. It just says, show us how to get to that answer. So you can use your union formula. The union here, these are inclusive events, so we use the formula with this subtraction of the intersection. However, in this case, we are given the union but do not know the intersection. So remember, when we have that formula, we can swap the intersection union, and now it's intersection here, union here. So let's use that formula. We know probability of A and B, we know the union, we add those up, subtract the union, and we get that value, which is we've confirmed it works. The reason it gave us that value is because even if you can't show how that works, you can now use that answer to answer the next part. Write down the value of Q and S. So Q, if all of A is 0.3, and now we know this part here is 0.2, then this must be 0.1. And again, if we know all of this is 0.6, and we know this is 0.2, then S must be 0.4. Finally, write down the value of probability of B naught. So B naught means everything outside of B. If B is 0.6, then everything outside of B is 0.4. Okay, next one, give this one a try. Okie dokie, let's take a look. This one is simpler than it might look. Let's take a look. So first thing to notice, it tells you the events are mutually exclusive. So if things are mutually exclusive, they look like this, right? There's no overlap, no intersection. So if you begin with the union formula, which we often begin with, you do not need the intersection bit. We're back down to mutually exclusive, which is just this bit. So just that part of the formula. To find the union, you just add up the two. All right, so in that case, we know our union is 0.5. We know probability of A is 0.2. We're looking for probability of B. It's the only unknown in this equation. We can solve it to be that. Pretty simple. Okay, next one, another third exam problem. Take a look, see if you can solve this. So this is a great problem for two reasons. Number one, it's talking about old Fiat taxis, probably in Italy, beautiful car, beautiful place. But the question is also a really good one, brings lots of probability ideas together. So we're looking for a taxi not being a yellow Fiat. So often when we have these not problems, it's best to look at them as, what about finding a yellow Fiat and then subtracting that one from 1, because that will tell us the ones that are not yellow Fiat. So what that means is this. If we're looking for yellow and Fiat, so not a yellow Fiat, then we can just say 1 minus probability of getting a yellow Fiat. Because if you subtract yellow Fiats from 1, you get the not yellow Fiats. So let's begin by finding yellow Fiats. And to find yellow Fiats, we can again go back to our normal union formula, but we're looking for the intersection, so we're going to swap the union bit with the intersection bit and go back to this formula. So now we're looking for intersection. We know yellow cars, taxis are 0.4, we know Fiats are 0.3, and we know the union, which it gave us here, taxi cab is yellow or a Fiat, or means union, 0.6. Calculate that, we get the intersection of 0.1. So now we know 0.1 of the time, or 1 out of 10, or 10% of cars are yellow Fiats. But we don't want yellow Fiats, so we do 1 minus the yellow Fiats. 1 minus 0.1 is 0.9. Awesome problem. Hope you were able to figure that out. Next, now to jump into this lesson, we're going to have an investigation that you will follow. The investigation has the classic situation of a coin toss, heads or tails, and a die roll 1 to 6. And here's our entire sample space diagram for that. Question 2 here, how many possible outcomes are there? I hope you said 12. We can see 12 possible outcomes right there. Next, question 3, try it out. So in this case, probability of getting ahead, well, heads are all along here. So that's 6 possibilities out of the 12. So probability of a head is 6 out of 12, or 1/2. That makes sense. Half of the things here are heads. Number 4, give it a try. Okay, so probability of getting L, which is less than 4, is all these choices here. All those represent rolls of less than 4. Sorry, less than 6. I'm sorry, less than 6. And that is 10 possibilities out of our 12 total, so 5 out of 6. Try 5. Now we're looking for the intersection of heads and less than 6. So here are heads and less than 6. So that is 5 choices out of the possible 12. Okay, question 6 is the key part of this investigation. It's to look for a relationship between these 3 values. So what connection do you see? And it means, by connection means, can you create a formula? Can you create a formula that connects those 3 things? Here we go. If you're able to come up with this, well done. The formula is probability of H intersection L equals probability of H times probability of L. And you can see how that works with these numbers. 1/2, which is H, 5/6, which is the L. Multiply those, you get 5/12, which is H and L. This is a very important rule, idea, and formula. It only works in a certain case, and the certain case it works with will be highlighted in question 7. So in question 7, we can say no. Less than 3 occurs 2/6 of the time. So here's 2/6 out of times if you roll ahead. Sorry, if you get ahead, or 2/6 of the time if you get a tail. So that 2/6 occurrence is not affected at all by your coin toss. So these kind of events where one event can happen and it has no influence on the probabilities of the other event are called independent events. And that's exactly what this formula is all about here. So let's move a little bit forward with this idea. So 2 events A and B are independent if the occurrence of one does not affect the chance of the other. And that's exactly what we saw here. So here in number 7, it was asking about getting less than 3, but before that we were talking about getting less than 6. The point is that, let's say you flip the coin first. Whether you get a head or tail on the coin has absolutely no impact on then when you roll the die, like what's the probability of getting less than 6 or less than 3 in this question. The coin toss has no effect on what happens with the die roll. The 2 things are separate of each other. They're independent of each other. So again, when we have in that experiment, rolling a die, flipping a coin, they're independent because the result of one has no effect on the result of the other. And for those, there's this rule. So based on the results of this investigation and what I've been talking about here, write down a rule to find probability of A and B if A and B are independent events. Okay, so hopefully this time around the rule was simpler because again it's alluding back to that rule we saw right here. And that rule tells us this, that if 2 events are independent, then probability of one and the other is just multiplying the probability of each. And this and, which we normally consider as and, in this kind of event or situation can be considered kind of like a then, like this occurs, then this occurs, or and like this occurs and this occurs at the same time, but it's kind of like one after the other. And in this case, we always multiply the 2. Let's look at an example of that. So here we have a die roll, and probability of getting a 6 we know is 1 out of 6. Now if you roll 2 dice, what's the probability of getting double 6? Well, it's 1/6, a 6 followed by another 6. So it's like 6 and 6, right? When those are independent, what you roll in this one has no effect on the probabilities of this roll. So 6 and 6, we can say 1/6 times 1/6 using this rule here, you multiply. All right, and that's 1 out of 36. Now what's the probability of getting a triple 6? So you roll 3 6s in a row. Well, it's 1/6 times 1/6 times 1/6, right? This thing happens, then this thing, then this thing. All these things are independent, so we just multiply and we get 1 over 216. Again, very important, this only works when the events are independent, where one has no effect on the outcome of the next one. So just multiplying the probabilities. Let's look at this thing in 2 ways, and this is important, I think, to look at it this way. Makes a really good connection with some previous things we've looked at. So again, here's your 2 die. Let's say you're rolling a blue die and a red die. Here's the blue rolls, here's the red rolls. You could fill all this with all the possibilities. We've seen this diagram many times. But here's rolling a double 1, here's rolling a 1 and a 2, and so on. Here's rolling a double 6, right? So rolling a double 6, we're looking at rolling a red 6 and a blue 6. Approach number 1, we say 6 and a 6. And we can look at it going back all the way to the basic probability definition, that the number of ways of getting a 6 and a 6 out of the number of ways of getting anything. So how many ways is there to get a 6 and a 6? Well, there's only one way, right? So the number of ways is one way to get a 6 and a 6. It's right here. And out of the entire sample space, all the possibilities here, there's 36 possibilities in the universal set, or the sample space. So one way here out of 36 is getting a double 6. That's kind of the old definition. And now looking at independent events, 6 and a 6 can be considered like rolling a 6 and then rolling a 6. So here's probability of rolling 1 6, 1 6, probability of rolling the second 6, 1 6, and we get multiply, and you get 136. The same thing, right? So whether we say, this one you can kind of think of, I rolled both dice at the same time, and I got one possibility out of 36 is that double 6. And here you can think of it as rolling one die first and then the next one. So like one die, then the next one, and you multiply. Same result, two different approaches. Really important to see the connection there. Okay, let's try the same thing here. See if you can answer this question here, thinking of now rolling a die and a coin. And die and coin, you know the sample space diagram. Here it is again. Here's the die, here's the coin, here's all our possibilities. See if you can answer this. Okay, we're going to look at this one just like the last one. If you use just a sample space diagram, probability of getting... Okay, so we're looking for probability of getting a tail and then a greater than 4. So using the sample space diagram, we have 12 possibilities, and a tail and greater than 4 is here. This is the only two possibilities where we have a tail and greater than 4. So 2, again, the number of ways of getting that is 2, and all the possibilities is 12. So 2 out of 12 is that, or 1/6. Now let's look at using the product rule. Okay, so now looking at the product rule, let me jump ahead to there. So looking at the product rule, you can look at it as one thing happening then the other. So first you're going to flip the coin and get a tail, and the probability of getting a tail is 1/2. And then you're going to roll the die, and the chance of getting greater than 4 is 2 out of 6. So now using product rule, we multiply those two independent events. 1/2 times 2/6 gives us 2/12, which is 1/6. The same answer is here. Again, both approaches, you should be familiar with both, and also just see the connection between those two things. Okay, here's another problem. Since we are studying probability, a responsible student carries around a sack of red, black, and blue cubes in it, since there's so many problems about pulling cubes from bags. So let's take a look. You draw a cube, return it to the bag. This is important here. Then draw another cube. Find the probability of selecting a red and a blue. Okay, try that. Here's the answer, red and blue. So red and blue can be red first, then blue, or blue first, then red. So there's two ways you should look at. So maybe you made this error of just looking at red then blue, but red and blue can be blue first, red second. So red then blue would be like this, probability of red times probability of blue, plus all the ways to get a blue first and then a red. So it's an or in the middle there, so we're going to add those two. So we have red 1/4, 1 out of 4 are red, and then times 5/12 blue. Plus, since we've returned all the cubes to the bag, sorry, here we've returned them also, so it's 12, and then 5/12 times 1/4. Okay, so that's that one, and we have an answer of 10/48 reduces to 5/24. Is this like rolling a double 6? Well, not quite, because when rolling a double 6, the first roll must be a 6, the second roll must be a 6. But in this case, we can draw a red blue or a blue red. So this is very different. With the double 6, we would have just done 1/6 times 1/6. We didn't have to worry about this adding thing, right? Because we got a 6 and a 6. Here we can get a red first, then blue, or a blue, then red, and that's very different. So let's look at this question now. It's changed a little bit. Now there are two sacks. Be careful, the contents have changed. You reach in simultaneously into each sack, drawing one cube. What is, first of all, what is better than carrying around a sack of cubes? Well, obviously it is carrying around two sacks of cubes. So here's our two sacks, and we have find the probability of selecting a blue and a black. So blue and the black, or maybe backwards also. Let's try it out. So in this case, blue and black can be made up of blue black or black blue, right? So in that case, blue black would be blue out of this one, 4/9 times 1/2, or from this one, if we do, sorry, or black first, so 1/3 times 3/10 blue, add those up, you get this value here. Last problem, try this out, and check all your work here. Hope that went